friend insists that waiting to add cold milk to your hot tea keeps the tea warmer for longer, allowing you to drink it at the perfect temperature exactly when you want it. You think he is just being pretentious and delaying your caffeine intake. It is time to settle this with thermodynamics and calculus. You brew exactly 250 grams of black tea at 95.0 degrees Celsius. You have exactly 25 grams of refrigerated milk at 5.0 degrees Celsius. Your office is a frigid 20.0 degrees Celsius. You consider your tea undrinkable until it hits a precise 60.0 degrees Celsius. You can either add the milk immediately in scenario A or wait, and add the milk later such that the final mixture instantly becomes 60.0 degrees Celsius in scenario B. The cooling of the liquid follows Newton's law of cooling, which states the rate of temperature change is proportional to the difference between the liquid's temperature and the ambient temperature. The constant of proportionality, K for your specific mug and liquid volume, is 0.045 inverse minutes. Assume the heat capacity of tea and milk are identical to water. The mug loses heat uniformly, and the act of pouring the milk is instantaneous, with no heat loss to the air during the pour itself. The question is not just who is right, but by exactly how many seconds does the optimal method save you from burning your tongue. We must calculate the total time elapsed from the moment the kettle finishes pouring until the moment the liquid in the mug hits exactly 60.0 degrees Celsius for both scenarios. We begin with the differential equation for Newton's law of cooling, which is the derivative of temperature with respect to time, equals negative K times the quantity temperature minus ambient temperature. By separating the variables and integrating, we find the time function equals 1 over K multiplied by the natural logarithm of the initial temperature difference divided by the final temperature difference. In scenario A, where milk is added immediately, we calculate the mixture temperature using a mass-weighted average. The sum of 250 grams at 95 degrees and 25 grams at 5 degrees divided by 275 total grams gives an initial mixture temperature of 86.818 degrees Celsius. Plugging this into our time equation with an ambient temperature of 20 degrees and a target of 60 degrees yields a total cooling time of 11.407 minutes. In scenario B, we must first calculate the precise temperature the tea must reach before we add the milk, so that the final mixture is exactly 60 degrees. Setting up the energy balance equation, where the final 60-degree mixture is composed of 250 grams of hot tea and 25 grams of cold milk. We solve for the required tea temperature and find it to be 65.5 degrees Celsius. We then calculate the time for the pure tea to cool from its initial 95 degrees down to this new threshold of 65.5 degrees in the ambient environment. The calculation yields a cooling time of 11.104 minutes. The difference between scenario A and scenario B is therefore 11.407 minus 11.104, which equals 0.303 minutes. Converting this decimal minute value into seconds by multiplying by 60 reveals that waiting to add the milk saves precisely 18.2 seconds. Your friend is technically correct. By delaying the milk until the tea reaches 65.5 degrees Celsius, you reach a drinkable 60.0 degrees Celsius roughly 18 seconds sooner than if you had added it right away. Whether 18